Newton's second law talks to us about how force, acceleration, and mass are related to each other. As it says here, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Newton's second law is one of the most important laws that we have in physics. There are other laws like the laws of thermodynamics and Einstein's special and general relativity, which play more significance and give us a lot more understanding about how the universe works. But Newton's second law describes basically how things move. Nothing will accelerate without a force. Usually in science classes, especially at the earlier grades, you find that F equals ma is the way that this equation is written. Unfortunately, that doesn't really describe how the equation was meant by Newton and how we should be thinking about it. We should be thinking about it as acceleration is proportional. Alpha, it means proportional to the force over the mass. In this form, it connects it back to our kinematics. For example, we have V final equals V initial plus AT. We can rewrite this as V final is equal to V initial plus F over M times T. But we aren't going to write it like that as much as we will just solve for A and plug it in. But in calculus form, thinking about it as this form will be something that could be useful to you if you go on to more advanced studies of physics. But Newton himself really was getting at the understanding of how acceleration is impacted by applying a greater push or pull. Push or pull meaning force. And so what Newton says is that if acceleration happens, something had to be pushing it. And depending on the mass or the inertia of the object, mass and inertia are the same, depending on the mass of the object, then the force could cause a big acceleration or the force could cause a little acceleration. This is a vector quantity, and that's going to give us some challenges over the next few weeks. Because as we are learning about Newton's second law, we are going to have a lot of different mathematical applications that we have to look at, a lot of different scenarios. So this simple equation is going to add a lot more challenge to us. All motion is caused by force applied to a mass causing acceleration. If something's moving, a force is applied. If something's stopping from moving, a force is applied. If something's being held up and not falling, a force is being applied. Force is what is making things happen. The units of force, because force in this form is equal to mass times acceleration, it would be a kilogram for the mass and a meter per second squared for the acceleration, leading to a kilogram meter per second squared. We define that idea of a kilogram meter per second squared with the Newton. It's a way of honoring the dead guy and also by simplifying it so that we don't confuse ourselves with the MKS values, kilogram meter per second squared. But remember, this is still based on something that can be measured with a balance, a stopwatch, and a ruler. Kilograms, meters, and seconds squared, those basic SI units, and we have just shortened it up by saying Newton. 1 Newton is equal to approximately a quarter of a pound. So if you go to McDonald's and ask for your Newton burger, really what you're asking for is your quarter pounder. So feel free to go there and say, hey, I'd like a Newton burger today. And that will help you remember this idea of 1 Newton is approximately a quarter of a pound. So 4 Newtons per pound is a good approximation. You'd be shy by a tiny bit, 9/10, but at least you would have a good approximation. Now, when we are talking about this concept of force, I want to give you a scenario. I said to you, acceleration is equal to force over mass. I want you to think of a shopping cart. You go into a store, and a grocery store, for example, and you have a shopping cart, and you can whip that shopping cart around very easily. You're applying a force. It has very little mass. And so because it has very little mass, the acceleration can be pretty big. But now you have a Now you have that same shopping cart with that same force, and you load it up with a big mass. When you do that, the acceleration becomes really small. It's harder to move that shopping cart. Same force, bigger mass, harder to turn the corner. Why? Because there's more inertia. It wants to keep doing what it's doing. If it's at rest, it's hard to get it started. If it's moving, it's hard to turn it or stop it. So big mass gives you a little acceleration, or a big mass requires a big force to get it moving. Likewise, if I have a big force and a small acceleration, then I get a small mass, then I get a big acceleration out. Big force, big acceleration with a small mass. So it's all proportionality. Keep that in mind. Here is a very basic problem that we can do. You can see here, this is a problem where we have a tractor pulling a wagon. The wagon has a mass of 275 kilograms, and the force is 440 newtons. So to solve this problem, we would set up our equation. What's the acceleration? We'd set up our equation. A is equal to F over m. So the acceleration is equal to 440 divided by 275. So our acceleration, when we do that, is going to be 1.6 meters per second squared. If we make this bigger, then the acceleration is less. If we make the force bigger and leave the mass the same, then the acceleration is more. If you have any questions, let me know.